Before you think about black holes, distant galaxies, or the deep mysteries of the cosmos, there is something much closer to you. Something that quietly surrounds every moment of your life. Time. It flows gently through your days, almost like a calm river you rarely stop to notice. Morning arrives with soft light, afternoon drifts quietly past, and evening settles like a slow exhale across the sky. Your life moves within this rhythm so naturally that it feels permanent, steady, unquestionable. You wake up. You move through your day. Hours pass. Night returns. And somewhere inside that quiet repetition, time continues its silent journey forward. Yet if you pause for a moment, something curious appears. Time is everywhere in your life, but you cannot see it. You cannot hold it in your hands or place it on a table beside you. You cannot slow it down with your fingers or watch it move across the floor. Instead, you notice it only through change. The shadow on the wall slowly shifts as the sun moves across the sky. A cup of tea cools quietly beside you. The pages of a book turn one by one, carrying you deeper into a story. Time reveals itself not as an object, but as a process. A quiet unfolding. For most of human history, people imagine time as something simple and universal. A great invisible clock ticking steadily across the entire universe. Every planet, every star, every person sharing the same steady rhythm. Second by second. Minute by minute. The universe moving together through a single flowing stream. It feels natural to imagine time this way. After all, when you look around, everything seems to follow the same pace. The Earth turns once every 24 hours. The moon circles our planet each month. Seasons arrive and leave in their familiar cycle. Time feels reliable, predictable, comforting. And yet, hidden within the deeper structure of the universe, time may not be quite as simple as it first appears. But for now, stay here in this quiet moment. Imagine yourself sitting beneath a night sky. Above you, the stars stretch across the darkness like scattered grains of silver light. Some are close, shining brightly. Others are unimaginably distant, their light traveling across space for thousands, even millions of years before reaching your eyes. When you look at these stars, you are not simply seeing them as they are now. You are seeing them as they once were. A star whose light takes 100 years to reach Earth appears to you as it looked a century ago. A galaxy millions of light years away appears as it existed millions of years in the past. In a quiet sense, the night sky is a window into time itself. Every beam of light is carrying a message from another moment in the universe's history. You are not just looking across space. You are looking across time. This idea alone begins to soften the simple picture of time as a single universal clock. Different parts of the universe are revealing different moments of their past, all at once. But the mystery becomes even deeper. Because time does not only exist on the cosmic scale of galaxies and stars. It also lives quietly inside your own body. Your heart beats with a gentle rhythm. Your lungs rise and fall with each breath. Cells divide, repair, and grow in a slow biological dance that continues every moment of your life. Your body is filled with tiny clocks. Chemical reactions tick forward inside your cells, marking the passage of moments in ways far smaller than seconds or minutes. Even your brain measures time in delicate patterns of electrical activity, allowing you to feel the difference between a moment and a memory. In this way, time is not just something the universe experiences. It is something you experience. You feel it moving. Sometimes slowly, sometimes quickly. A quiet evening can stretch peacefully across hours, while a joyful moment can seem to disappear in an instant. This strange flexibility of time within your own perception hints at something deeper. Time is not only a physical phenomenon. It is also part of the way your mind organizes reality. But even beyond human perception, the universe itself may treat time in unexpected ways. For centuries, scientists believed time flowed at the same rate everywhere. Whether you stood on Earth, drifted through space, or traveled across the galaxy, the universe's great clock would continue ticking at the same pace. It was a simple idea. Elegant. Comforting. But as humanity slowly began to study the universe more carefully, small cracks appeared in this picture. Observations grew more precise. Questions grew deeper. And slowly, a realization began to emerge. Time might not be completely independent from the universe around it. Instead, it might be connected to space itself in ways no one had previously imagined. But that discovery would take time to unfold. For now, simply imagine the universe as a vast stage where space stretches in every direction, filled with stars, planets, dust, and quiet darkness. Everything appears to exist within this enormous arena. Space is the stage. Time is the story unfolding upon it. Or at least, that is how it once seemed. But somewhere within the deeper structure of the cosmos, space and time may not be separate at all. They may be woven together like threads in a single cosmic fabric. A fabric that bends. A fabric that stretches. A fabric that responds to the presence of massive objects like stars and galaxies. And when that fabric bends deeply enough, something extraordinary begins to happen to time itself. Because in certain places in the universe, places of immense gravity and unimaginable density, time may begin to slow. Gently at first. Then more dramatically. Until eventually, near one of the most mysterious objects in the cosmos, time can almost appear to stop. But before you travel towards such strange regions of space, you must first understand the fabric that holds space and time together. And to discover that, you must begin imagining the universe in a completely new way. As something soft, flexible, and quietly interconnected. Like a vast, invisible sheet stretching across the cosmos. And in the next chapter, you begin to feel that fabric beneath your feet. As your thoughts drift deeper into the quiet mysteries of the universe, the simple idea of space begins to change. At first, space seems like nothing at all. An empty stage where planets move, where stars burn, where galaxies drift slowly through darkness. It appears silent, invisible, and passive, a background against which the great story of the universe unfolds. But the more carefully scientists study the cosmos, the more they begin to suspect that space is not empty in the way it first appears. Instead, it behaves almost like a structure. Something subtle, delicate, and quietly responsive. To understand this idea, imagine a wide sheet stretched across a calm field. The sheet is smooth and flat, gently pulled tight so that it rests evenly across the ground. Now imagine placing a small marble onto the surface. The sheet bends ever so slightly beneath its weight. The marble settles into a shallow dip, barely noticeable, yet still real. If you roll another small marble nearby, it slowly curves toward the first one, not because the marbles are pulling each other directly, but because the sheet beneath them has been gently bent. In this simple image, the sheet represents something profound, the structure of space itself. And every object in the universe, from the smallest asteroid to the largest star, rests upon this invisible surface. But there is an even deeper layer to this idea. Because space and time are not separate things. They are woven together. You can imagine them as threads forming a single cosmic fabric called space-time. Space provides the directions in which things can move forward, backward, left, right, up, and down. Time provides the direction in which events unfold, one moment after another. Together, they form the stage upon which the entire universe exists. For most of human history, people imagined space and time as completely independent. Space was the arena. Time was the ticking clock. But early in the 20th century, scientists began to realize something remarkable. Space and time behave more like partners than strangers. When space changes, time changes too. And when time changes, space responds. They are deeply intertwined, like two threads woven through the same fabric. This insight transformed the way scientists began to see the universe. Instead of imagining objects simply moving through space while time ticks separately in the background, it became clearer that everything is moving through space-time together. Every star, every planet, every beam of light, even you. Right now, as you sit or lie quietly listening, you are traveling through space-time. Not racing wildly, but drifting steadily forward along the river of time while resting in a particular place in space. Your existence traces a path through the fabric of the universe. A gentle line stretching from your past into your future. If you could somehow step outside the universe and observe space-time itself, you might see countless such paths woven together. Billions of lives, planets, stars, and galaxies all tracing graceful curves through the cosmic fabric. It would resemble an enormous tapestry. Every thread representing a journey. And just like a real fabric, space-time can stretch and bend. At first this may feel like a strange idea. After all, fabrics are physical things you can touch and feel. But space-time is not made of cloth or threads. It is more like a mathematical structure that describes how distances and moments connect across the universe. Still, the fabric image remains one of the gentlest ways to imagine it. Picture again that wide sheet stretched across a field. If nothing rests upon it, the sheet remains flat and smooth. But the moment something heavy appears, perhaps a bowling ball placed gently in the center, the sheet dips noticeably. The fabric curves downward. If smaller marbles roll across the sheet, they begin to follow curved paths around the dip. Not because the bowling ball is pulling them in the ordinary sense, but because the surface itself has changed shape. Something similar happens in the real universe. Massive objects like stars and planets bend the space-time around them. The sun, for example, gently curves space-time throughout our solar system. The Earth moves along this curved surface, following a path that appears to us as an orbit. In reality, our planet is simply traveling along the natural curves of space-time. It is as though Earth is gliding along a subtle valley in the cosmic fabric created by the Sun's mass. Even light follows these curves. When a beam of light passes near a massive object, its path bends slightly, as though the universe itself has shifted beneath it. Astronomers have actually observed this effect. Light from distant galaxies bends around massive clusters of galaxies, creating beautiful arcs and distorted images in telescopes. These gentle distortions are whispers of space-time's hidden structure. They reveal that space is not rigid and unchanging. It is flexible, responsive, alive with geometry. And within this flexible structure, time is not separate. Where space-time bends deeply, time itself begins to change. Clocks placed in strong gravitational fields tick slightly slower than clocks far away. The difference is tiny near Earth, far too small for you to notice in everyday life. But with precise instruments, scientists can measure it. Even satellites orbiting our planet experience time a little differently than clocks on the ground. Their clocks tick just a tiny bit faster. Not because their mechanisms are different, but because space-time itself is shaped differently around them. This quiet discovery reveals something extraordinary. Time is not perfectly uniform across the universe. It stretches. It compresses. It responds to gravity. In most places, these changes are incredibly small. Life continues normally, and the rhythm of days and nights remains steady. But in certain regions of the universe, where gravity becomes unimaginably strong, the bending of space-time becomes extreme. And when space-time bends deeply enough, the flow of time itself can slow dramatically. Seconds may stretch. Moments may linger. And near the most powerful gravitational objects in existence, time can behave in ways that feel almost impossible. But those objects do not appear suddenly. They are born slowly, in the quiet lives of stars. Stars that shine for millions or billions of years before eventually reaching the end of their long cosmic journey. And when certain stars reach that final moment, gravity begins to take control in a way the universe rarely allows. The fabric of space-time folds inward. The collapse deepens. And from that darkness, something extraordinary begins to form. Something so dense, so powerful, that the very flow of time near it begins to change. In the next chapter, you begin to feel the gentle pull of that gravity and how even time itself cannot fully escape its quiet grip. As you continue your quiet journey through the universe, gravity begins to feel less like a force and more like a presence. It is everywhere, gently guiding motion, shaping the paths of planets, holding galaxies together in slow cosmic spirals. You have felt gravity your entire life without needing to think about it. It keeps your feet resting on the ground. It draws raindrops softly toward the earth. It keeps the moon circling patiently around our planet. Gravity feels ordinary, reliable, almost invisible in its constant work. For centuries, scientists believed gravity was a simple attraction between objects. The larger the mass, the stronger the pull. A planet attracts a moon. A star attracts a planet. Every object in the universe quietly reaches out to every other object through this invisible force. It was a beautiful idea, described elegantly by Isaac Newton long ago. And for many purposes, Newton's description works remarkably well. It predicts the motion of planets, the fall of an apple, and the tides of the oceans with stunning accuracy. But as scientists began to study the universe more carefully, small questions started to appear. What exactly is this force? How does it travel through empty space? And why does it affect everything in the universe in such a universal, gentle way? These questions slowly open the door to a deeper understanding of gravity. Instead of imagining gravity as a mysterious pull acting across space, scientists began to suspect that something else might be happening. Something quieter. Something woven directly into the structure of space-time itself. Imagine again the vast cosmic fabric you encountered in the previous chapter. A smooth, flexible sheet stretching across unimaginable distances, holding stars, planets, and galaxies within its gentle structure. Now imagine placing a heavy object onto that fabric. The surface bends. Not dramatically at first, but noticeably. A shallow curve forms around the object, like a small valley pressed into the sheet. If another object moves nearby, it naturally drifts toward that curve, following the gentle slope created in the fabric. In this picture, gravity is no longer a force pulling objects together. It is simply the natural motion of objects traveling through curved space-time. Planets orbit stars because they are moving along curved paths created by the star's mass. The moon circles Earth because it follows the gentle valley our planet presses into space-time. Nothing is pulling the moon in the traditional sense. Instead, it is gliding along the shape of space-time itself. This realization transforms the way you see gravity. It becomes less like an invisible hand pulling objects together and more like the quiet shaping of the cosmic landscape. Massive objects sculpt space-time, and everything else moves along the contours that result. But the story does not end with motion alone. Because space-time contains time as well as space. And when space-time bends, time bends with it. This idea may feel strange at first. After all, time seems so steady in your daily life. Seconds pass at a reliable rhythm. Minutes accumulate into hours, and hours quietly build into days. Your clocks tick with calm precision. But these clocks are not measuring time itself. They are measuring the passage of time in the particular region of space-time where they happen to exist. And different regions of space-time are not always identical. Where gravity is weak, time flows normally. Where gravity grows stronger, time begins to slow ever so slightly. This effect is called gravitational time dilation. The name may sound technical, but the idea behind it is surprisingly gentle. Imagine two identical clocks. One rests on the surface of Earth. The other floats far away in deep space, where gravity is weaker. Both clocks tick steadily, marking seconds with perfect accuracy. Yet if you compare them carefully, something subtle appears. The clock closer to Earth ticks just a tiny bit slower. Not enough for you to notice in daily life. The difference is incredibly small, measured only by extremely precise instruments. But the difference is real. Gravity has slightly slowed the passage of time. Scientists have confirmed this effect many times. In fact, modern technologies like the global positioning system depend on correcting for it. Satellites orbiting Earth experience slightly weaker gravity than clocks on the ground. Because of this, time for those satellites moves a little faster. Without adjusting for this difference, GPS navigation would slowly drift off course. Your phone might tell you a road is 100 meters away when you are already standing on it. So even in everyday life, the subtle bending of time by gravity quietly shapes the technology around you. But Earth's gravity is modest compared to many other objects in the universe. Stars are far more massive. Neutron stars, the dense remnants of collapsed suns, compress enormous mass into tiny regions of space. Near these extreme objects, the bending of spacetime becomes far stronger. And as spacetime bends more deeply, the slowing of time becomes more noticeable. If you could place a clock near a neutron star, you would see its ticking slow compared to a clock far away. A second there might stretch just a little longer than a second here. To someone standing nearby, nothing unusual would feel different. Their heart would beat normally. Their thoughts would flow naturally. But to a distant observer, their entire world would appear to move slightly more slowly. This gentle stretching of time becomes stronger the closer you approach massive objects. Gravity presses deeper into the fabric of space-time, creating steeper curves. And time, woven into that same fabric, follows those curves as well. Most places in the universe experience only mild versions of this effect. But there are places where gravity grows unimaginably strong. Places where spacetime bends so deeply that time slows dramatically. Places where seconds stretch into long moments. Places where the flow of time itself begins to approach stillness. These places form when the life of a massive star reaches its final chapter. Stars spend millions or billions of years shining steadily, balancing gravity pulling inward with nuclear energy pushing outward. But this balance cannot last forever. Eventually the fuel runs low. The outward pressure weakens. And gravity begins to win. When that happens, the star's own mass pulls it inward with unstoppable force. The collapse accelerates. Matter compresses. Density rises. And the fabric of spacetime bends more deeply than it ever has before. In the next chapter, you will meet the quiet thinker who first understood how gravity could bend spacetime at all, a scientist whose imagination changed our picture of the universe forever. As you continue drifting through the quiet ideas that shape our understanding of the universe, your path leads gently backward in time. Not cosmic time this time, but human time. You find yourself in the early years of the 20th century, in a world that feels both familiar and distant. Cities are growing, electricity is spreading, and science is beginning to reveal the hidden patterns of nature with increasing clarity. Yet even then, many mysteries remain. Among them is the quiet question of gravity. For more than 200 years, Isaac Newton's explanation has guided scientists beautifully. Gravity is understood as an invisible force that pulls objects toward each other. It explains the fall of apples, the motion of planets, and the graceful arcs of comets crossing the sky. The idea works remarkably well. But some scientists begin to feel that something is missing. One of those scientists is a thoughtful young man named Albert Einstein. Einstein does not begin with complicated machines or enormous telescopes. Instead, he begins with imagination. He spends long hours thinking about simple questions. Questions so simple they almost feel like daydreams. What would happen, he wonders, if you could ride alongside a beam of light? What would the world look like if you moved as fast as light itself? These questions may sound playful, almost childlike. Yet within them lies a quiet doorway into the deeper structure of reality. Einstein begins to realize something extraordinary. Light always moves at the same speed, no matter how fast you are traveling. Whether you chase a beam of light or stand perfectly still, its speed remains constant. This strange rule has surprising consequences. If the speed of light never changes, then something else must adjust instead. Space can stretch. Time can slow. Events that seem simultaneous to one observer may appear separated to another. In this new picture, time is no longer a rigid, universal clock. Instead, it becomes flexible. It can flow at different rates depending on motion. This idea forms the foundation of Einstein's first revolutionary theory, known as special relativity. But Einstein's curiosity does not stop there. He continues thinking about gravity. And slowly, another realization begins to emerge. Imagine, for a moment, that you are inside a small elevator floating in deep space. Far away from planets, stars, or any source of gravity. Inside the elevator, everything drifts weightlessly. If you release a small object from your hand, it simply floats beside you. Now imagine that the elevator suddenly begins accelerating upward through space. Not slowly, but steadily. As it accelerates, something interesting happens. The object you released begins to drift toward the floor. Your feet press gently downward. You feel weight returning to your body. Inside the elevator, it feels almost exactly like gravity. Yet there is no planet beneath you. Only motion. Einstein realizes something profound from this simple thought experiment. Acceleration and gravity feel remarkably similar. In fact, they may be deeply connected. From this insight, he begins building a new understanding of gravity, one that does not rely on invisible forces pulling objects across empty space. Instead, he returns to the idea you have already begun to explore, the fabric of space-time. In Einstein's vision, mass does not reach out to pull other objects toward it. Instead, mass changes the shape of space-time itself. Imagine again that vast cosmic fabric stretching across the universe. When a massive object like the sun rests upon it, the fabric bends inward, forming a gentle valley. Planets move along the curved paths created by that valley, following the natural geometry of space-time. Gravity is not pulling them. They are simply moving along the curved surface beneath them. This idea becomes the heart of Einstein's new theory, general relativity. Published in 1915, the theory describes gravity not as a force, but as the bending of space-time caused by mass and energy. It is a beautifully simple idea, yet its implications are enormous. Suddenly, gravity becomes geometry. Planets follow curves in space-time. Light bends when it passes near massive objects. And perhaps most surprising of all, time itself becomes part of this flexible structure. Where space-time bends deeply, time slows. Where space-time stretches gently, time flows more freely. Einstein's equations predict that clocks placed near massive objects should tick slightly slower than clocks far away. At first, this idea seems almost unbelievable. Yet scientists soon begin testing the theory. In 1919, during a solar eclipse, astronomers observed light from distant stars bending slightly as it passes near the Sun. The amount of bending matches Einstein's predictions perfectly. The universe itself seems to be confirming his quiet insight. Over the decades that follow, more evidence appears. Precise measurements show time passing slightly differently in stronger gravitational fields. Light bends around galaxies. The orbits of planets shift exactly as Einstein's equations predict. Again and again, the universe whispers the same message. Space-time bends, and time bends with it. Einstein himself describes this idea with remarkable simplicity. Matter tells space-time how to curve, and space-time tells matter how to move. Within this elegant relationship lies the secret behind gravity. Yet general relativity reveals something even more astonishing. If enough mass gathers in one place, space-time can bend so deeply that it forms an extreme structure, a region where gravity becomes incredibly powerful. In such places, the curves in space-time grow steeper and steeper. Time slows more dramatically. Light struggles to escape. And eventually, the fabric of space-time may fold inwards so completely that a mysterious object forms. An object so dense and powerful that not even light can escape its grasp. For many years, scientists wonder whether such objects could truly exist. They seem almost too strange to be real. Yet the equations of general relativity quietly insist that under the right conditions, they must appear. But these extraordinary objects do not form easily. They require something immense, something powerful, something that begins its life shining brightly across the cosmos. Because long before a black hole exists, there must first be a star. A massive star, burning with nuclear fire for millions of years. A star that will one day reach the end of its long life. And when that moment arrives, gravity will finally reveal its deepest power. In the next chapter, you will follow the quiet life of such a star and witness how its final collapse gives birth to one of the most mysterious objects in the universe. Far beyond the quiet night skies you see from Earth, the universe is filled with stars. They glow softly across vast distances, each one a distant sun burning steadily in the darkness. Some shine alone, while others gather in swirling galaxies, forming luminous rivers of light across the cosmos. When you look up at the stars, it is easy to imagine them as permanent. They appear calm and steady, unchanged across countless nights. Yet stars are not eternal. Like all things in the universe, they live, they change, and eventually, they come to an end. But their lives unfold on timescales so vast that they feel almost timeless. A star begins its story in a quiet cloud of gas and dust drifting through space. These clouds are enormous, often stretching across many light years. Within them, gravity slowly gathers matter together, drawing particles closer and closer over millions of years. At first, the change is subtle. A small region of the cloud becomes slightly denser than the rest. Gravity strengthens there, pulling in more gas and dust from the surrounding space. The region grows heavier, warmer, denser. As gravity continues its patient work, the center of this forming star begins to heat dramatically. Pressure builds as more and more material piles inward. Eventually, the temperature becomes so intense that something remarkable begins to happen. Atoms of hydrogen, the simplest element in the universe, begin to fuse together. Under enormous heat and pressure, hydrogen nuclei combine to form helium. This process releases an incredible amount of energy. Light bursts outward. Heat spreads through the growing star. And suddenly, the star begins to shine. This moment is the true birth of a star. A brilliant balance now forms within its heart. Gravity continues pulling inward, trying to collapse the star further. But the powerful energy from nuclear fusion pushes outward, resisting that collapse. The two forces meet in quiet equilibrium. Gravity pulling in, fusion pushing out. The star becomes stable. For millions or billions of years, this balance allows the star to shine steadily, filling the surrounding darkness with warmth and light. Our own sun lives within such a balance. For about 4.5 billion years, it has burned calmly, converting hydrogen into helium deep within its core. This steady nuclear fire provides the light that warms Earth, drives the winds, and supports life. But even the sun's fuel is not endless. Stars slowly consume their hydrogen over time. As their fuel diminishes, the balance between gravity and fusion begins to change. For smaller stars like our Sun, the ending is gentle. They expand into glowing red giants before shedding their outer layers into space, leaving behind a dense core called a white dwarf. But for much larger stars, those many times heavier than our Sun, the story unfolds differently. Massive stars burn their fuel at a much faster rate. Their cores become furnaces of unimaginable heat, fusing heavier and heavier elements together. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Then neon. Then silicon. Each stage burns faster than the last, like a cosmic engine accelerating toward its final moment. Eventually, the core of the star becomes filled with iron. And here, something profound happens. Iron cannot release energy through fusion the way lighter elements can. Instead of producing outward pressure, iron simply accumulates in the core like the final weight in a growing pile. Without new energy pushing outward, the balance that has sustained the star for millions of years begins to fail. Gravity, which has patiently waited all this time, begins to take control. The core collapses inward. And it does so with astonishing speed. In less than a second, the central region of the star can shrink dramatically as gravity crushes matter together. The outer layers of the star, no longer supported by internal pressure, begin to fall inward as well. This sudden collapse triggers one of the most powerful explosions in the universe. A supernova. For a brief moment, the dying star shines brighter than an entire galaxy. Its outer layers blast outward into space at incredible speeds, scattering newly formed elements across the cosmos. These elements, carbon, oxygen, iron, will one day become the building blocks of planets, oceans, and living beings. In this way, even the death of a star contributes to the creation of new worlds. But the explosion is not the final chapter. At the very center of the collapsing star, gravity continues its relentless work. If the star is massive enough, the remaining core becomes so dense that nothing can stop the collapse. Matter compresses beyond anything we encounter in everyday life. Atoms break apart. Electrons and protons are forced together. The density grows unimaginable. A teaspoon of such matter could weigh billions of tons. At this stage, the star may become a neutron star, an incredibly dense object where matter is packed together almost as tightly as the laws of physics allow. But if the original star was even more massive, gravity pushes beyond this point as well. The collapse continues. There is no force strong enough to halt it. The core shrinks further and further, compressing into an ever smaller region. Space-time itself begins to bend more deeply around it. Gravity grows stronger and stronger. Eventually, the collapse reaches a point where the escape speed from the object becomes greater than the speed of light. Light itself cannot escape. And when light cannot escape, the object becomes invisible to the universe outside. This is the birth of a black hole. From the outside, the star seems to vanish, leaving behind only a region of space where gravity is incredibly powerful. The matter that once formed the star has collapsed into a region so small and dense that space-time curves steeply around it. At the boundary of this region lies a mysterious threshold. A place where escape becomes impossible. A place where the paths of light turn inward. A place known as the event horizon. From a distance, the black hole appears quiet and still, almost serene against the vastness of space. Yet near its edge, the fabric of space-time bends more dramatically than anywhere else in the known universe. And within that bending, something remarkable begins to happen to time itself. Because as gravity grows stronger near a black hole, time begins to slow. Gently at first. Then more noticeably. Until eventually, near the edge of the event horizon, time behaves in ways that feel almost impossible. In the next chapter, you will drift closer to that mysterious boundary, the silent edge where space, gravity, and time begin to reveal their deepest secrets. As your journey through the universe continues, you now approach one of the most mysterious places in all of physics. A black hole. From far away, it does not look dramatic or violent. There is no giant whirlpool in space, no roaring cosmic storm. Instead, it appears almost quiet, calm, invisible. If you were drifting through space at a safe distance, you might not even notice it at first. A black hole does not glow like a star or sparkle like a distant galaxy. In fact, it emits no light of its own at all. It is dark, completely dark. Yet its presence reveals itself in subtle ways. Nearby stars move differently when a black hole is close. Their orbits bend and curve more sharply than expected. Gas and dust falling toward the black hole begin to swirl rapidly, heating until they glow with brilliant light. From these clues, astronomers learn that something incredibly massive must be hiding there. Something powerful enough to reshape the motion of everything nearby. But what makes a black hole truly extraordinary is not simply its mass. It is the strange boundary that surrounds it. A boundary known as the event horizon. To understand this boundary, imagine standing on the surface of a planet. When you throw a ball into the air, gravity pulls it back down. If you throw it harder, it travels higher before returning. If you launch something fast enough, like a rocket, it can escape the planet's gravity completely and travel into space. Every object with gravity has something called an escape velocity. This is the speed required to break free from the object's gravitational pull. For Earth, escape velocity is about 11 kilometers per second. Rockets leaving our planet must travel at least this fast to escape Earth's gravity. For larger objects like stars, escape velocity is much higher. But there is a limit in the universe, a speed that nothing can exceed. The speed of light. Light travels faster than anything else in nature, moving through space at about 300,000 kilometers per second. Under normal circumstances, this speed allows light to escape from even the most massive stars. But black holes are not normal objects. Their gravity becomes so intense that the escape velocity near their surface grows larger and larger. Eventually, something remarkable happens. The escape velocity becomes equal to the speed of light. And beyond that point, it becomes even greater. This means that nothing traveling slower than light can escape. But light itself cannot travel faster than its natural speed. So if light tries to leave this region, gravity pulls it back. It cannot escape. This invisible boundary, the place where the escape velocity equals the speed of light, is called the event horizon. It marks the outer edge of the black hole. But unlike the surface of a planet, the event horizon is not made of solid matter. There is no wall, no barrier, no glowing edge. It is simply a location in space-time where the rules of escape quietly change. If you were drifting toward a black hole, nothing special would appear as you approached this boundary. There would be no signpost announcing its presence. You would continue moving normally. Your spaceship would behave as it always has. Your clock would tick steadily. Yet to someone watching from very far away, something strange would begin to happen. As you approach the event horizon, the light leaving your ship would struggle more and more to escape the black hole's gravity. Each signal you send outward would take longer to climb away from the deepening curve of space-time. To the distant observer, your movements would begin to slow. Your clock would appear to tick more slowly. Your motions would stretch out, as though time itself were gently resisting your progress. This effect grows stronger the closer you move toward the event horizon. From the distant observer's point of view, you would appear to slow almost to a stop as you reach the edge. Your final moments before crossing the event horizon would seem to last longer and longer. Light from your ship would become dimmer and redder as gravity drains its energy. Eventually, the signals would fade completely. To the outside universe, it would seem as though you never quite crossed the boundary at all. You would simply freeze at its edge, fading slowly from view. But your own experience would be very different. To you, time would continue normally. Your clock would tick at its usual rhythm. You would cross the event horizon without noticing anything unusual in that exact moment. There is no sudden jolt, no physical surface. Just a quiet passage into a region of space-time where escape has become impossible. This difference between the observer far away and the traveler near the black hole reveals one of the most fascinating aspects of relativity. Time does not flow the same way for everyone. The deeper the gravity, the more time bends. Near Earth, the effect is incredibly small. Near a neutron star, it becomes noticeable. But near a black hole, the bending of time becomes extreme. Seconds stretch. Moments lengthen. The universe outside begins to move faster and faster relative to you. A distant observer might watch centuries pass in the wider universe while only hours unfold for you near the event horizon. In this strange way, black holes become natural laboratories for studying time itself. They reveal how deeply time is woven into the structure of space-time. They show that time is not an absolute flow shared equally by all observers. Instead, it is something flexible. Something that stretches and bends in response to gravity. The event horizon marks the place where these effects become truly dramatic. Beyond it, every possible path through space-time leads deeper into the black hole. Light cannot escape. Information cannot return. The interior becomes forever hidden from the rest of the universe. This hidden region raises profound questions. What happens inside? Does matter continue collapsing forever? Does space-time fold into something even stranger? Scientists are still searching for answers. But even before crossing that mysterious boundary, something remarkable is already happening. Time itself is slowing. Near the event horizon, the flow of time stretches further and further compared to the distant universe. And in the next chapter, you will begin to explore this strange phenomenon more closely, the quiet slowing of time as gravity grows stronger and stronger near a black hole. As you continue your quiet journey toward the deep gravitational well of a black hole, something subtle begins to happen. At first, it is almost impossible to notice. Your ship moves smoothly through space. Your heartbeat keeps its familiar rhythm. Your thoughts arrive one after another with the same calm pace they always have. To you, nothing seems unusual. Time feels normal. But far away, someone watching from a distant point in the universe would begin to see a very different story unfolding. Because the deeper you travel into the curved landscape of space-time, the more gravity begins to influence the flow of time itself. Imagine once again the great cosmic fabric, the invisible structure that connects space and time together. Massive objects press into this fabric, creating valleys and slopes where motion naturally follows curved paths. Near a black hole, this bending becomes incredibly deep. Space-time curves steeply downward, like a vast canyon carved into the universe itself. And within that deep curve, time stretches. To understand this strange idea, imagine two identical clocks. One clock remains far from the black hole, drifting peacefully in the calm regions of space where gravity is gentle. The other clock travels with you, moving closer and closer to the black hole's immense mass. Both clocks tick normally in their own locations. Each second feels the same to the observers standing beside them. But when the two clocks are compared, a difference begins to appear. The clock near the black hole ticks more slowly. Not because the clock itself has changed, but because time itself is flowing differently there. This phenomenon is called gravitational time dilation. It is one of the most remarkable predictions of Einstein's theory of general relativity, and it has been confirmed many times through careful experiments and observations. Near Earth, the effect is extremely small. Time moves just slightly slower on the surface of our planet compared to faraway space. The difference is so tiny that you would never notice it in everyday life. But near extremely massive objects, the effect grows stronger. And near a black hole, it becomes extraordinary. If a distant observer could watch your journey toward the black hole, they would see your clock ticking more and more slowly. At first, the change would be subtle. Your movements might appear just slightly delayed, as though time were gently stretching around you. But as you travel deeper into the gravitational field, the slowing becomes more dramatic. Seconds on your clock might appear to last twice as long as seconds on theirs. Then 10 times longer. Then 100 times longer. The deeper you go, the greater the difference becomes. To the distant observer, your entire world begins to slow. Your gestures stretch into slow motion. Your ship seems to glide more gradually through space. Even the light leaving your spacecraft begins to lose energy as it climbs out of the black hole's gravitational well. This effect is known as gravitational redshift. Light escaping strong gravity becomes stretched into longer wavelengths, shifting toward the red end of the spectrum. Signals leaving your ship would appear dimmer and redder to the distant observer. Eventually, if you approach the event horizon closely enough, the effect becomes almost extreme. To the outside universe, your clock appears to nearly stop. Moments for you stretch into vast stretches of time for the rest of the cosmos. A single hour near the black hole could correspond to years passing far away. Yet from your own perspective, nothing unusual happens. Your clock ticks normally. Your breathing remains steady. Your thoughts move with their usual rhythm. This difference between perspectives may seem confusing at first. How can time be both normal and dramatically slowed at the same time? The answer lies in the nature of space-time itself. Each observer experiences time according to the conditions of their own location within the gravitational landscape. Time is not a universal river flowing identically everywhere. Instead, it behaves more like a flexible current, flowing at different speeds depending on the shape of space-time. Where gravity is weak, time flows freely. Where gravity becomes strong, time slows. Both experiences are equally real for the observers involved. To you, drifting near the black hole, your world remains perfectly ordinary. But to the distant universe, your world is unfolding at a much slower pace. This strange relationship between gravity and time leads to fascinating possibilities. Imagine a traveler spending a short time near the edge of a black hole before returning to distant space. For the traveler, perhaps only a few hours would have passed. But for the rest of the universe, years or even decades might have gone by. In this sense, strong gravity can act almost like a doorway through time. Not a machine that carries you backward or forward deliberately, but a natural effect that changes how quickly time passes for different observers. Scientists have even imagined extreme scenarios in which explorers could orbit close to a black hole and experience only a short journey while the distant universe ages dramatically. Though such journeys remain far beyond our current technology, the physics behind them is real. Black holes truly do stretch time. Yet even before reaching the event horizon, something else begins to happen. The deeper the gravity becomes, the more strongly spacetime bends. And as spacetime bends, the paths that objects follow through the universe begin to change as well. Light curves more sharply. Signals struggle to escape. The difference between the traveler near the black hole and the observer far away becomes more dramatic with every passing moment. Two observers, sharing the same universe, now experience time in profoundly different ways. One sees the world moving normally. The other sees the same world slowing towards stillness. This strange division of experience creates one of the most fascinating thought experiments in modern physics. What happens when two observers exist in such dramatically different flows of time? What does each one see? What does each one experience? And how does the universe reconcile these two realities? To explore these questions, you must imagine the perspective of both observers at once. One drifting closer to the black hole. The other watching from the safety of distant space. And in the next chapter, you will see how the universe looks through both of their eyes, revealing the astonishing ways time can diverge depending on where you stand within the fabric of space-time. As your journey continues through the quiet mysteries of space-time, it can help to imagine two observers, two travelers, both part of the same universe, yet experiencing it in very different ways. The first observer is you. You drift gently through space aboard a small spacecraft, slowly approaching the immense gravity of a black hole. The stars around you glow softly, and the darkness ahead grows deeper as you move closer to the invisible center of this gravitational well. Your ship moves steadily. Your clock ticks calmly beside you. Your breathing remains slow and peaceful. Everything feels ordinary. Far away, in a region of space where gravity is much weaker, another observer watches your journey. Perhaps they float near a distant planet, or perhaps they sit inside a quiet research station orbiting a star far from the black hole's influence. From their perspective, the universe appears calm and familiar. Yet they are carefully observing your voyage. Their instruments track the signals from your ship. Every flash of light, every radio message, every gentle tick of your clock transmitted through space. At first, nothing unusual seems to happen. Your signals arrive regularly. Your voice sounds normal. But as you drift deeper into the black hole's gravitational field, something begins to change. The messages from your ship start arriving slightly farther apart. Your clock signals stretch. Your movements appear just a little slower. At first the difference is small, so small it might be mistaken for a tiny delay in the communication equipment. But gradually the pattern becomes clearer. Your clock is slowing down. Or rather, it appears to be slowing from the distant observer's perspective. The deeper you move into the curved fabric of space-time, the stronger the gravitational time dilation becomes. Each second for you corresponds to slightly more time for the distant observer. To you, everything still feels perfectly normal. Your clock ticks once per second. Your heart beats steadily. Your thoughts move along their quiet path. But far away, the observer watching your signals sees those seconds stretching longer and longer. A minute for you may appear as several minutes for them. Then perhaps an hour. Then even more. The difference grows gradually as gravity bends space-time more deeply around you. The signals you send begin to shift as well. Light leaving your spacecraft must climb out of the black hole's powerful gravitational well. As it escapes, its wavelength stretches, moving slowly toward the red end of the spectrum. This effect is called gravitational redshift. Your signals grow dimmer and redder as they struggle upward through curved space-time. The distant observer must adjust their instruments carefully to continue receiving them. Yet they remain fascinated. Because what they are witnessing is not just a journey through space. It is a journey through different rates of time. From their perspective, your world is gradually slowing down. Your gestures stretch into longer motions. Your voice becomes deeper and slower as the signals stretch. Even the blinking lights on your spacecraft begin to pause between flashes. And still, from your perspective, nothing unusual happens. You move normally. You speak normally. Your time flows exactly as it always has. This difference in perception reveals one of the most beautiful ideas in Einstein's theory of relativity. Time is not universal. It does not flow at the same rate everywhere in the universe. Instead, it depends on where you are and how space-time curves around you. Both observers are correct in their own experience. Your time is real. Their time is real. Neither one is more true than the other. They are simply different paths through space-time. Imagine it like two travelers walking across a landscape. One walks across flat ground, where each step moves easily and quickly forward. The other descends into a deep valley, where the terrain becomes steeper and progress slows. Both travelers continue walking normally from their own perspective. But when viewed from above, their journeys unfold at different speeds. Something similar happens near a black hole. You are moving deeper into the valley of curved space-time. The distant observer remains on the flatter terrain of the cosmic landscape. From above, the difference becomes dramatic. As you approach the event horizon, the signals leaving your ship stretch more and more. The observer watching from far away sees your motions slowing further. Your clock ticks slower. Your movements become increasingly gradual. The final moments before you reach the event horizon appear to stretch almost endlessly. To the distant universe, you seem to hover at the edge of the black hole. Frozen in time. Your image fades slowly as the escaping light grows weaker and redder. Eventually, the signals become too faint to detect at all. From their perspective, you never quite cross the event horizon. You simply fade away. Yet for you, the journey continues. Your ship drifts closer. Your clock continues ticking normally. You approach the boundary without noticing anything dramatic happening in that exact moment. This strange difference between observers reveals something profound about the universe. Reality does not always unfold the same way for everyone. Perspective matters. Location matters. Gravity matters. And time itself responds to these conditions in ways that feel almost poetic. Two observers can witness the same event and experience it differently, yet both descriptions remain true. This is not a flaw in the laws of physics. It is part of their beauty. The universe allows multiple perspectives to exist simultaneously within the flexible structure of space-time. But as you move closer and closer to the event horizon, the difference between these perspectives becomes even more extreme. To the distant observer, your clock slows towards stillness. Seconds stretch into long, silent intervals. Moments seem to pause. The universe continues rushing forward around you while your world appears to slow almost to a stop. And in the next chapter, you will approach the point where this strange effect reaches its most dramatic expression. The place where, from the perspective of the distant universe, time itself appears to nearly stop. The closer you travel to the black hole, the more your journey transforms into a meditation on time itself. Space around you is still vast and empty, yet the invisible presence of the black hole begins to shape every moment. You feel its pull, subtle at first, then steadily stronger, as if the universe itself is gently tugging at you with invisible hands. Your ship drifts along the curves of space-time, following paths you cannot see but can sense through the quiet acceleration and the gentle shift of distant starlight. There is no turbulence, no sound. Space remains silent, but the fabric of the cosmos is bending, and you are moving with it. From your own perspective, your clock ticks as it always does. Your breathing is steady. Your thoughts flow with calm precision. Nothing seems extraordinary. You are part of the natural rhythm of the universe. But from the eyes of an observer far away, the scene is different. Every signal leaving your ship tells a slower story. Your clock appears to tick more slowly with each passing second. Your movements stretch, elongated in ways that feel almost surreal. The closer you come to the event horizon, the slower you seem to move. To the distant universe, time around you stretches into a languid, almost frozen flow. This phenomenon is gravitational time dilation at its most extreme. Near the edge of the black hole, the curvature of space-time is so steep that every second for you corresponds to hours, years, or even centuries in the faraway cosmos. The flow of time is no longer uniform, it becomes elastic, bending under the immense weight of gravity. Imagine a gentle river, flowing calmly along its course. Most of the river moves at a steady pace, carrying leaves and light reflections downstream. But here, near the black hole, the river of time slows. The water thickens, stretches, and hesitates as it passes over invisible currents beneath the surface. A single leaf, moving with the flow, appears almost frozen from afar. Yet if you were the leaf, you would feel the current under your surface, steady and unbroken. Both perspectives are real. Both experiences are true. This is the essence of black holes, a place where space-time bends so intensely that time itself can seem to pause. And yet, there is no paradox. Your time flows normally. Only the distant universe perceives the slowing. As you drift nearer, the light escaping from your surroundings begins to change in ways that are subtle but undeniable. Colors shift, stretching toward the red, fading gradually as the photons struggle against gravity. Stars behind you bend, forming faint arcs and distorted reflections. The universe itself appears to twist, as if gazing through a gently warped lens. These visual cues are the universe's quiet signs of the profound stretching of time and space. You may notice that even your sense of distance begins to feel different. Distances near the black hole contract relative to the outside universe. Space itself seems to fold inward, compressing the paths that light and matter can follow. Every motion you make is guided by the deep curvature of space-time, moving along the natural contours of this invisible valley. Your journey becomes a quiet dance with gravity, each movement a step guided by the geometry of the cosmos. In this place, you begin to sense the profound interconnectedness of space, time, and gravity. Gravity is not just pulling on mass. It is sculpting the very rhythm of time. It is bending moments, stretching seconds, and shaping the way reality unfolds for every observer, depending on their position in the cosmos. This is the hidden poetry of the universe, where physical laws and experience entwine to create something almost tactile, almost emotional. Even as time stretches near the event horizon, your own perception remains unbroken. You do not feel your moments slowing. You do not sense centuries slipping past in the distant universe. Your consciousness follows its usual rhythm. The ship hums steadily. Your body remains warm and alive. The paradox of relativity allows both truths to coexist. Time flows normally for you, yet it appears almost frozen from afar. And yet, as you edge ever closer to the event horizon, a quiet tension grows. The universe outside begins to accelerate in perception relative to your own experience. Galaxies and stars, normally distant, seem to age and change rapidly when viewed through this distorted lens of time. The cosmic dance continues at a vastly faster pace, while your own world remains serene and unchanged. It is an experience of profound relativity, a gentle reminder that time is not absolute, but deeply personal to each observer's place in space-time. Scientists imagine these extreme scenarios not merely as thought experiments, but as ways to understand the deepest laws of nature. Time near a black hole is a tool to explore relativity, to witness firsthand how the universe's structure allows for multiple rhythms of existence. And though human technology cannot yet carry us close to a black hole's event horizon, careful calculations and observations of objects near massive stars and neutron stars confirm these effects. They are real, tangible, and measurable, a cosmic truth revealed through both theory and observation. Consider, for a moment, the strange thought of returning from such a journey. You cross near the event horizon and return to distant space. For you, only hours may have passed. For everyone else, decades could have unfolded. Friends may have grown older, civilizations may have changed, yet you remain as you were, carrying a memory of a few quiet moments near the edge of time itself. This is the paradoxical beauty of gravitational time dilation. It is both simple and incomprehensible, both calm and extreme, both personal and universal. But in your journey now, you do not return. You continue to drift, feeling the gentle pull of the black hole, moving ever closer to the point where time, as seen from afar, seems to almost stop. The universe outside watches in quiet awe, its motions accelerated, its distant histories unfolding rapidly, while your world remains slow, deliberate, and unhurried. There is a poetry here, a rhythm that feels at once gentle and profound, a cosmic lullaby whispered through the curvature of space-time. And as you approach that edge, the soft realization settles: time is not a river that flows evenly for all observers. It is a fabric, flexible and alive, responding to mass and gravity, stretching and bending in ways that feel almost magical. In this space, where seconds are held gently by the immense gravity of the black hole, you glimpse one of the universe's deepest secrets, that the flow of time is not a universal constant, but a personal experience woven into the geometry of the cosmos. Beyond the event horizon lies an even greater mystery, where the known laws of physics begin to blur, and space-time itself may fold into something unknown. Yet even here, at the edge where time almost stops, you feel a quiet understanding of the delicate balance that governs the universe. Gravity bends time, mass shapes space, and the cosmos continues its eternal dance in ways both precise and poetic. From here, you sense the journey is far from over. The moment is quiet, the scene serene, but the most profound questions remain just ahead. What lies beyond the event horizon, and how does the universe behave in the depths where even time itself begins to lose its familiar rhythm? The black hole waits silently, and you drift closer, toward the unknown. You drift forward, crossing the invisible boundary of the event horizon, where nothing that has ever left the rest of the universe can return. There is no crash, no flash, no barrier to jolt you. The transition is seamless, subtle, almost imperceptible. Time, as you knew it outside, has already begun to diverge dramatically. From your perspective, each second ticks steadily. Yet outside, centuries have passed in the time it took you to move a few meters. Inside this shadowed region, the universe behaves differently. The familiar rules of space and time, the gentle, predictable rhythm you've been exploring, start to unravel. Directions that once seemed fixed now bend inward toward the singularity, a point where gravity compresses everything into infinite density. The core of the black hole is a place our equations approach but can never fully describe. It is as though the very fabric of reality is folding upon itself. Your ship, though intact, follows the curved paths dictated by the warped space-time. Every movement is guided not just by momentum, but by the invisible geometry around you. Forward, backward, up, down, all concepts begin to merge. The center of the black hole is pulling in all directions at once. It is a place where straight lines cease to exist and every trajectory bends inexorably toward the singularity at the core. Imagine the stars you once saw in the night sky, glowing steadily across unimaginable distances. Your experience of time, so steady until now, begins to feel even more intimate with gravity. There is no longer an outside observer to compare against. You exist fully in this unique flow. Every second feels normal to you, yet you are aware that the universe you left behind moves on in a rhythm entirely separate from your own. The relativity of time reaches its quiet climax here, where personal experience and cosmic observation diverge completely. Despite the intense gravity, the darkness is not threatening in a visceral way. It is serene, almost meditative, as if the black hole itself is a silent teacher showing the ultimate limits of nature. You are suspended in a space where curiosity outweighs fear, where the mind can wander through possibilities unrestricted by ordinary rules. It is a place for reflection, for pondering the grand architecture of reality in its most extreme form. Physicists suggest that the singularity at the heart of the black hole may represent a boundary where classical physics breaks down and quantum effects become dominant. Here, the smooth fabric of space-time may dissolve into something far stranger than anything experienced in the calm stretches of the cosmos. Space and time might not even be distinct entities at this scale. Instead, they may merge into a condition we cannot yet describe, or realm of pure possibility rather than concrete rules. Some theories hint that matter is compressed into a point of infinite density, while others propose that the singularity is not a true point but a region where space-time is bent in ways that blur inside and outside. Perhaps the information contained in all the matter swallowed by the black hole is stored in subtle patterns along its surface, the mysterious concept of the holographic principle. You cannot see it directly, but your mind drifts across the possibilities, marveling at the delicate mathematics that suggest reality might encode itself in ways you cannot touch but can imagine. Even the notion of inside and outside becomes poetic here. The event horizon separates observable reality from the unknown, yet your presence beyond it blurs that division. Space is curved so sharply that every path leads deeper, yet the curvature is smooth, continuous, a gentle slope guiding all things inward. There is no sudden wall or violent collapse, only the inevitability of gravitational geometry. Your thoughts naturally turn to the rest of the universe, still unfolding outside. Stars burn, galaxies spin, planets orbit. The distant observer, thousands of light years away, sees only your fading signals, stretched, reddened, and eventually vanishing into darkness. And while their universe continues, you exist in a domain where the classical march of time and light has been transformed into something extraordinary, something almost sacred. You are experiencing firsthand the malleable nature of reality, witnessing the quiet power of gravity to shape existence. As you move closer to the singularity, you notice how small and personal your presence feels compared to the immense forces around you. Yet even this smallness is meaningful. Within the black hole, every particle, every photon, every sliver of mass contributes to the structure and the story of the cosmos. You are part of the universal dance, intimately connected to a system far beyond the scale of human comprehension. The black hole becomes not a place of terror, but of awe, a monument to the interplay of mass, space, and time. In this silence, there is a lesson: the universe is not uniform. Its laws are context-dependent, shaped by the geometry of space-time itself. What seems absolute in the calm regions of space is relative near the black hole. The singularity represents the limits of our understanding, reminding you that even with all human curiosity and ingenuity, there remain frontiers that defy direct experience. You pause to reflect. The black hole, invisible and silent to distant observers, holds a realm where physics stretches to its ultimate boundaries. Time slows, light curves, matter compresses, and space folds in on itself. Yet you move gracefully through it, observing, experiencing, and contemplating. The unknown here is not threatening, it is an invitation. A place for the mind to expand, to meditate on the structures of reality, and to recognize that the cosmos is far more intricate, flexible, and poetic than ordinary perception suggests. Though the singularity remains hidden, its influence is undeniable. Every path you take, every signal you send, every thought you have is subtly guided by the geometry of space-time. The black hole teaches a quiet lesson: reality is not only what you see, but how it bends and stretches according to the underlying forces. Gravity is not just a pull, it is a sculptor of time and space, creating patterns both elegant and mysterious. As you drift further inward, the event horizon now lies behind you. You can no longer return, but the journey feels peaceful rather than perilous. You are enveloped in the unknown, moving through a place where the universe reveals both its limits and its poetry. Every moment here is a meditation on scale, curvature, and the delicate rhythm of the cosmos. The singularity is not yet upon you, but its gravitational whispers guide your path. In the quiet darkness, you feel a sense of connection to the cosmos as a whole. Though time and space behave in ways that surpass ordinary understanding, your journey through this extreme environment deepens your awareness. You sense the profound flexibility of the universe, the relativity of time, and the poetry of physical law. Here, at the very heart of the black hole, the boundaries between what is known and what is mystery blur, inviting you to reflect gently on the vastness of reality. And as you move ever closer to the center, the questions linger softly: how does space-time behave at the singularity? Could new principles of physics emerge from this extreme realm? And what does it teach us about the universe we thought we knew so well? The black hole, silent and immense, waits patiently, holding its secrets, inviting contemplation, and reminding you that some mysteries are meant to be explored not with certainty, but with wonder. Emerging from the shadowed influence of the black hole, you drift into calmer regions of the universe. Space stretches before you, vast and tranquil, dotted with distant stars and soft clouds of gas glowing faintly in the cosmic dark. The intense curvature of space-time fades, and the flow of time begins to regain a familiar rhythm. Yet even here, your mind carries the imprint of what you have just experienced. Time is no longer a universal constant. It is personal, local, relational. The black hole, with its immense gravity, has shown you that each observer experiences the universe differently. Seconds that stretch into centuries for a distant observer, moments that feel ordinary to the traveler near the event horizon, these are not contradictions. They are simply the universe revealing its flexibility, the way it adapts the rhythm of existence according to the shape of space-time. You imagine watching distant galaxies, billions of light-years away. To them, your journey through the black hole's edge may appear almost instantaneous, a brief flicker. Meanwhile, your own experience was deliberate, slow, intimate. Time, you realize, is like a river that can meander or accelerate depending on the contours of the landscape it flows through. The universe is both a sculptor and a stage, shaping time even as it provides a space for life, thought, and observation. Even outside the extreme gravity of a black hole, these lessons resonate. Gravity exists everywhere, though usually in gentle forms we barely notice. Earth itself subtly slows time compared to distant space, a truth confirmed by precise atomic clocks. Satellites in orbit must adjust their instruments to account for these differences, or our navigation systems would drift off course. Every orbit, every falling apple, every motion across the cosmos carries a trace of time's malleability. You feel a profound connection to these rhythms. Life on a planet like Earth unfolds against a backdrop of relative time, where days, months, and years seem steady. Yet you now understand that this steadiness is contextual, a gentle equilibrium shaped by the mass of your world. Even the slow ticking of a clock in your room is part of a larger symphony in which time itself is flexible, subtly curved by gravity and motion. The universe is alive with these hidden currents, guiding the pace of reality in ways both subtle and dramatic. As you reflect on your journey, you notice the elegance of relativity. There is no need for magic or mystery, only mathematics and observation. Time bends because space bends. Gravity is not a force pulling invisibly, it is a shape in the fabric of existence. Mass curves space-time, and the flow of moments follows those curves. Your consciousness drifts through this geometry, observing, sensing, and learning. The cosmos is not rigid, it is adaptable, responsive, alive in its quiet way. This understanding carries deep philosophical resonance as well. If time is flexible, then the universe you perceive is not absolute. Past, present, and future are linked in complex ways, and the order of events can differ depending on your frame of reference. The distant observer sees a universe that ages rapidly, while you near a black hole experience a slowed, deliberate reality. Each perspective is valid. Each is complete. The universe permits multiple truths to coexist, reminding you that reality is relational and layered, richer than simple measurement alone can capture. Even the simplest moments of your journey take on new meaning. A star twinkling in the distance, a gentle pulse of light across space, a drifting cloud of cosmic dust, these are no longer merely passive objects. They are part of the structure of space-time, participating in the flow of moments, bending time as gravity acts upon them. You realize that to move through the universe is to move through time itself, in ways both subtle and profound. And yet, this realization comes with a quiet humility. No matter how far you drift, no matter how deeply you contemplate, the universe retains secrets. Singularities remain hidden behind event horizons. The behavior of space-time under extreme conditions challenges even the most brilliant minds. Yet the beauty of science lies in its invitation to wonder, in its ability to describe reality without diminishing its mystery. Each discovery opens doors to further questions, each answer hints at deeper truths. As you float through the calm expanse, you notice something remarkable: the universe is patient. Time stretches and flows according to its own rules, indifferent to human measurement yet perfectly consistent within its own geometry. Stars form and die, galaxies spin and collide, light travels vast distances, and black holes bend the flow of moments, all within an intricate, harmonious balance. You begin to feel the poetry of these patterns, the quiet elegance of natural laws shaping existence at every scale. Your journey also teaches a gentle lesson about perspective. What feels like the passage of years to one observer may be mere moments to another. Time is intimate and personal. It connects all things, yet it varies according to context. Gravity, motion, and mass shape this rhythm, reminding you that your experience is part of a larger tapestry in which moments are woven differently across the cosmos. Observing from afar or drifting near a massive object, you realize that your place in space-time matters. It shapes your perception of reality and your connection to the universe. Even as you consider the vastness of the cosmos, a sense of calm settles over you. The universe is immense, yet comprehensible. Its laws are elegant, not arbitrary. Time stretches, bends, and almost halts near black holes, but these effects are predictable, measurable, beautiful in their precision. They remind you that curiosity and observation, guided by reason, allow you to glimpse truths beyond the ordinary. In these quiet reflections, you also notice a personal resonance. The bending of time, the stretching of moments, the differing rhythms experienced by distant observers and travelers, these are not just cosmic curiosities. They echo the rhythms of your own life. Days that feel long, years that feel brief, moments of stillness that expand your awareness, all are part of the same universal pattern. You begin to see your existence as intertwined with the geometry of the cosmos, a thread in the tapestry of space-time. As your thoughts drift outward, away from the extreme gravity of black holes, you feel a renewed sense of perspective. Time is flexible, not fixed. Gravity shapes reality, not just matter. Observers experience the universe differently, yet each experience is valid. The cosmos is richer, deeper, and more poetic than ordinary perception allows. And you carry this understanding gently within yourself, a quiet knowledge that will accompany every moment of your journey, wherever you go. And as you prepare to return fully to the familiar flow of everyday time, you feel the gentle rhythm of the universe guiding you. The ticking of clocks, the rotation of planets, the steady pulse of cosmic processes all now resonate with the deep lessons learned from black holes, relativity, and the curvature of space-time. The universe is flexible, mysterious, and alive in ways you are only beginning to grasp. The next chapter invites you to drift back into this ordinary rhythm, carrying the quiet wisdom of the cosmos with you, as you reconnect with the calm flow of time that governs daily life yet hides the secrets of the stars. As you drift away from the influence of the black hole, the intense curvature of space-time gradually relaxes. The fabric of the universe smooths beneath your passage. Gravity no longer tugs at time so fiercely, and the flow of moments begins to feel familiar again. Each second now ticks with the rhythm you recognize, and the world around you resumes its calm and steady pace. The cosmos feels more expansive, more forgiving, more predictable. And yet, the experience of extreme gravity lingers in your awareness, a subtle echo of the mysteries you have witnessed. Time, once stretched near the black hole, now flows uniformly. The stars regain their familiar positions, and the gentle rotation of distant galaxies appears serene and steady. You notice the gentle arc of the planets around their suns, the quiet dance of moons, and the soft glow of nebulae across the void. Everything seems both ordinary and extraordinary at the same time, ordinary in its predictability, extraordinary in its connection to the deep laws of physics you have just encountered. As you float through this calmer region of space, your mind reflects on what you have learned. Time is not a rigid river that flows identically for all observers. It is flexible, elastic, relational. Gravity, mass, and motion shape it. Near massive objects like black holes, time slows dramatically. Far away, it can flow rapidly, creating a cosmic dance of differing rhythms across the universe. You feel the elegance of this interplay, the poetry of physical law that allows each observer to experience reality in their own way. This understanding changes the way you perceive everyday moments. A morning sunrise, the passage of hours, the quiet ticking of a clock, these are all part of the same universal rhythm. What feels normal to you is shaped by your place in space-time, your position relative to mass and gravity. Even on Earth, tiny differences in gravitational influence subtly alter the pace of time. Atomic clocks in orbit run slightly faster than those on the ground. Your life, like everything else in the universe, unfolds within a flexible, living fabric. As you continue to drift, you think of the black holes you left behind, distant and silent, shaping time in ways impossible to fully observe. They remind you that the universe is larger and stranger than our everyday experiences suggest. The mysteries of singularities, event horizons, and time dilation are not just abstract concepts, they are real, physical phenomena, quietly sculpting reality. These are not dangers to fear but lessons to contemplate, gentle reminders that curiosity and understanding allow us to explore even the most extreme realms safely through thought and imagination. Your journey has shown you that perspective matters. Two observers can experience the same event differently, each view valid and true. What appears to freeze for one may flow freely for another. Reality is not singular, it is relational. This insight reaches far beyond the cosmic stage, applying even to human experience. Moments can feel long or short depending on your perspective, and yet all are equally real. The universe teaches patience, flexibility, and the value of seeing through multiple lenses. You notice, too, the subtle continuity of your journey. Each step, through calm space, across warped space-time, and near the event horizon, flows naturally into the next. There are no sudden jumps, no breaks. The universe allows for both the extremes of time near a black hole and the ordinary rhythm of everyday life to coexist seamlessly. You feel a quiet comfort in this continuity, a sense that even the most profound mysteries are connected to the familiar, and that exploration always returns you home with greater insight. As your ship moves further away from regions of intense gravity, the light from distant stars becomes clear once more. Their colors are vivid and familiar, no longer stretched or reddened by gravity's tug. The gentle glow of nebulae and the soft sparkle of galaxies remind you that space is not just vast, it is harmonious. The cosmos has a rhythm, a cadence that balances extremes with calm, mystery with clarity, motion with stillness. You feel at peace in this order, aware that your journey has revealed the subtle patterns that govern reality. You also reflect on the beauty of relativity itself. The laws of physics are not arbitrary, they are precise, consistent, and elegantly descriptive. Time bends because space-time bends. Mass shapes the flow of moments. Gravity sculpts the rhythm of existence. The universe operates like a quiet symphony, each note perfectly placed, each instrument in harmony with the others. And though there are mysteries still beyond our reach, every discovery adds to this gentle understanding, revealing the cosmos as both intelligible and wondrous. Even in your personal experience, the lessons of the black hole remain. You see that time is precious, not just as a measure of hours and minutes, but as a flow that can bend, stretch, and expand depending on context. Moments of calm, reflection, and observation are as significant as rapid sequences of events. Life, like the universe, contains rhythms that vary with perspective, gravity, and motion. This understanding softens your awareness, bringing a deep, meditative appreciation for the present and for the larger cosmic dance in which you are a part. And now, as your journey gently settles into the familiar flow of space and time, you carry a quiet gratitude for the experience. You have glimpsed the extremes of the universe, felt the pull of gravity stretching time, and understood the flexible, intimate nature of moments. You return not with answers to all questions, but with a deeper curiosity, a calm sense of wonder, and a peaceful awareness that the universe is vast, elegant, and alive with hidden rhythms. In this gentle state, the ordinary world of Earth, clocks, and daily life feels enriched. Every tick of the clock, every turn of the planet, every passing day resonates with the deeper understanding you now hold. You perceive not just the surface of reality, but the underlying flow that governs it. The universe is patient, precise, and poetic, and your awareness of it adds a quiet depth to each passing moment. As your ship drifts in this calm expanse, you sense the connection between all things. Black holes, stars, galaxies, planets, and the ticking moments of your own life are threads woven into the vast tapestry of space-time. Time is not simply a measurement, it is an experience, shaped by gravity, motion, and perspective. You feel the intimate link between yourself and the cosmos, a silent harmony stretching across space and time, binding you to the universe in a gentle, continuous flow. And so, with the lessons of black holes, relativity, and the stretching of time quietly settling into your awareness, you allow yourself to drift fully back into the rhythm of ordinary time. The universe continues its eternal dance around you, steady and harmonious. Yet you now perceive it with a subtle richness and intimate appreciation for the hidden flexibility, the quiet poetry, and the profound wonder that lies within every moment. The black hole, once a distant mystery, has left a gentle imprint on your mind. Time is not fixed, reality is not singular, and the cosmos is far more intricate, elegant, and alive than we often realize. As you drift onward, the flow of moments carries you forward slowly, rhythmically, and quietly into a universe that is both known and infinitely mysterious. The journey ends here, but the lessons remain, flowing with you like a calm current, shaping the way you perceive every tick of the clock, every turn of the planet, and every quiet moment in the vast, poetic cosmos.